Uh, it's great to see you and thank you for being here. I know some of you are planning your migration from SAS 9 to Vaya, whereas some of you are already on Vaya running in production. So irrespective of where you are in that journey, we have heard the same question: how do we preserve the performance and application behavior that we relied on with stored process while migrating to Vaya, which is a cloud native Kubernetes platform, right? And that's exactly what we will tackle today. So I have an informative agenda lined up for you. First, I will go over a short comparison between the two platforms. Then I will look at a couple of challenges that we have heard from customers. Then I will introduce you to a couple of newer capabilities that we have in Vaya to resolve those challenges along with short demos. Then finally, I will share some best practices that you can take away from this session. I hope that sounds exciting. Let's get started. So the first thing that you will notice is when you migrate a SAS 9 stored process to Vaya is that the stored process is now a SAS Vaya job. In SAS 9, you executed the stored process on either a stored process server or a workspace server, but in Vaya, you would be running it on a SAS compute server. In SAS 9, you edited the authoring using Enterprise Guide or SAS Management Console, but in Vaya, you would be authoring it using SAS AI and Data Studio or SAS Job Execution Web App. There are some newer capabilities in Vaya, such as editing task prompts in either JSON or HTML, and there is also a better REST API support for job execution in Vaya. While there are a lot of familiar use cases, whether it is capabilities, whether it is regular use cases or the job output formats that are supported or the URL-based execution path that you are all familiar with, the main difference though is how the job is orchestrated and how the resources are provisioned to execute these jobs. And how the resources are provisioned does lead to the first challenge that we have heard from our customers. That is, after migrating to Vaya, the stored process performance, the execution performance being slow, especially for short duration jobs. And that is because when you migrate to Vaya, the default configuration, the job is processed through job execution service. And this service is built for resiliency, result persistence, and elasticity. That means to run that job, a new compute server is spun up. Because a new compute server is spun up to execute this job, there is a cold start delay. So this orchestration overhead often dominates the execution speed. And we have seen customers reporting several seconds to complete the stored process. And that is one of the challenge. Then for short running jobs, the orchestrator overhead often dominates this speed, right? And our customers are basically reporting several seconds, while the SAS program itself can run under a second or in milliseconds. And in Vaya, we have introduced this concept of reusable compute server, which are pre-started servers where you can ideally cut down the cold start delay. However, the overhead the job execution service adds is noticeable. And we know majority of stored process are short duration, interactive use cases where speed is critical. So that's the first challenge. The second challenge is lack of support for stored server functions and macros, which prevented customers from running some key use cases, such as creating applications where using multi-step workflows, where maintaining session state across job requests are needed. Similarly, session initialization and termination code processing. So we have now solution in Vaya to address both these challenges, and I will look into that next. Let me first introduce to compute task, which is our answer to the first challenge on execution performance. Compute task provides a new and faster execution path in Vaya for running stored process, and it is available since Cadence 2025-09. So it is a new and faster execution path for short duration jobs, And when I say short duration, it is something that you can complete in a couple of seconds. There are three key characteristics of compute tasks that I want to highlight. One, it is synchronous in nature. That means you can run a SAS program and receive its output in the same HTTP request call. The second, it needs a reusable compute server as this execution engine. As you know, these are pre-started servers, so we are cutting down on the cold start delay. And the third, it provides multi-part input and output support. That means the inputs and outputs are exchanged in multi-part form data in the same HTTP request. So the result is the execution performance that is closer to the SAS/NAND performance your end users are used to for short duration jobs. And when working with compute tasks, there are some design constraints that you need to be aware of. Compute task has a timeout, and the default is 5 seconds, but you can configure it up to maximum 30 seconds. So it is not suitable for long-running, fault-tolerant workloads. So if there is any HTTP connection issues, the client or the end user will need to resubmit to complete that request. Now, enabling compute task is very straightforward, and you can do that using SAS Job Execution Web App. There are two job definition parameters that are important here. Number one is the compute context. So the job must be configured to run on a compute context that is using reusable compute servers, as I mentioned. And the second one to note is the underscore execution task parameter. So the value needs to be set to true, and these two configuration changes will ensure that the execution path for your migrated store process is now via compute task, right? So as you can see, no code changes is needed here. It is only the metadata level decision that you will make to configure it to run via compute task. So let me switch to a demo, and I want to walk you through two scenarios here. First, let me show you how easy it is to switch your via job to execute using compute task, as well as I'll run couple of STP examples, store process examples, and we will measure the performance. So here I'm logged into Vaya, and we are at the SAS job execution endpoint, which basically loads the job execution web application. And for the first use case, I will use a typical stored process web UI use case where an output is streamed directly to the web browser. Then the STP program main aisle, it basically loads a landing page for an example custom online library application. And it uses a data step basically to render the HTML. And as you can see here, the HTML is rendered using the web-out file rep option, and the output will look like this. And when you migrate an STP stored process over, by default, it is configured to run using the SAS job execution compute context, so which will basically run using the job execution service that I mentioned earlier. So in this default configurations, let's go ahead and run this. So I'm switching to the URL path execution method where I have enabled the developer tool here to measure the performance. So I'm running it now. It is basically spinning up a new compute pod behind the scenes and loading the necessary images, and it took 8.27 seconds to complete this, right? For my execution use case, speed is critical because it's an interactive use case. So let me now switch to run the same stored process using compute task. So I'll go back to the job execution service. So from properties, I'll first change the compute context to run using the reusable context, a context that my admin had created earlier. Then I'll go to the parameter section, and I will change the underscore execution task parameter, set the value to true. So these two changes will ensure that now I am running this using compute tasks. So with that change, let's go back to the URL execution path. And before I run it, let me go clear the previous time. And now if you run it, we see that it completed in 420 milliseconds, right? So this is how you supercharge the stored process after migration to bring the speed that your end users are used to when running in SAS 9. The other example that I want to walk through is a common reporting use case. So here the data for the report is coming from a library connection, and I created this profit pie chart using Enterprise Guide and migrated it over to Vaya. And the library connection definition is pointing to a SAS data set that I hosted on a NFS volume mount. And if we see this STP program, we see that it is using a couple of procs, proc template as well as proc SG render to basically render the pie chart using the financial summary data set. And it also uses a couple of macros to generate this data. And I have already configured this to run using compute tasks. So here you see it's pointing to reusable context as well as underscore execution task parameter is set to true. So with that, let me go ahead and run it. Let me clear the previous time there. And when I run it, we'll notice that it completed under a second, right? So these two examples will basically show you that switching to use compute task will bring you the speed, and that's how you can supercharge your stored process execution. Next, let me walk you through the second challenge about feature parity and the functionality that we have added in Vaya to address that challenge, right? So with 2025-11 release, we have added support for STP server functions, select set of functions and macros, and you can see the list here. If in SAS 9, if you had an example where you used STP SRV functions, that is now an equivalent support available in Vaya. And you don't have to make any code change as part of the migration. You can bring those programs and it will run smoothly in Vaya. And with the addition of STP SRV session function, it is now possible to maintain session state across multiple STP requests as long as they are using the same session. So how does this feature work? Basically, the macro variables and data can now survive from one call to the next. And this is extremely beneficial for customers who are looking to build custom applications where it uses multi-step workflows. For example, a shopping cart ordering system, right? And the key notable here is that this capability works for both job execution service-based execution path as well as compute task-based execution path. And you can use the STP SRV session create function to persist the session as well as the delete function to remove the session after your use case is completed. And it saves all the global macro variables. The data sets and catalogs are basically persisted across this request using the save library, which is a temporary library that is created during the session. And with that, let's go and take a look at how this is working through a demo. So the use case that I will demo is the same online library custom application that I referenced earlier. The online library custom application is a set of 5 STPs. So here in this folder sessions, I have 5 STPs that are configured for this application use case. And I have already set up to run each one of them through compute task because speed is critical here. So I have defined as the default configuration for all these 5 STPs after migration. And the main aisle, that is the landing page of the online custom library. And here I am creating the STP SRV session using the create function. And this data step basically renders 4 different aisle cards for me, starting with book to hardware. And you can see it is pointing to the aisle STP passing passing type as a parameter. And if we examine the aisle STP, we see that this STP is basically showing all the items belonging to that particular aisle. And the data for this is coming from a SAS data set that I have mounted on an NFS volume. And the data step here is basically creating URLs for each of those items. So you see here an example of I'm creating a URL for each of this item, and the URL is pointing to add item STP. And if you look at the add item STP, this is basically appending that item that being selected to the save library that I referenced earlier. Save.cart is the library that I'm creating, and these items are getting appended there using proc append. And I can view shopping cart at any time. Basically, it will use proc print to display all these items that are added to the save library, right? And logout STP is basically simulating a checkout experience for me. And in the end, what is important to note is when this STP is executed, it is the session is deleted, right? So I've completed my entire user flow there. So with that understanding, let's go and see this in action. So here is the landing page where you see all those 4 different aisle cards getting displayed from books to hardware aisle. So I click on that aisle STP, it loads the items that are belonging. So this data is coming from the SAS data set. So the URL is pointing to the add to cart STP. So let me go ahead and add one item. So you see this confirmation that item has been added. Let me go back and add one more item to the cart. So switch to a different aisle and add another item there. So I can now go and look at the shopping cart. So this will basically pull all the items from the save library and the proc print display you can see here. And the other thing to note here is if you examine the browser URL, right, the session ID is being persisted across the session execution. Both session ID as well as the program, that is the program or the stored process that is being executed for this, right? So let me now go and add one more item from the hardware aisle. So this is item number 4. And we can see the shopping cart now. It has 4 items. Let me go ahead and check out. The library checkout is complete. The logout call is called, right? So basically that is the use case wherein which you see if you have a use case where multi-step workflows is needed, it is now possible. You can migrate your programs over to Vaya and provide the similar user experience in Vaya as well. So let me switch to run some, tell you some best practices. The first best practice is choosing the right execution path. So this is important, and it all depends on your use case. If you have, for example, a long-running scheduled batch job, right, executing it through the default configuration, that is the job execution service, which spins up new compute pod, that is the best approach because it is cost efficient and resilient, right? But if you do want a better performance, you can look to switch to using job execution service with reusable compute server, and that will cut down the cold start delay time that I mentioned earlier. So this is an interactive analytics use case. It provides resiliency, result persistence, and improved performance. However, if your goal is speed, that speed is the critical point here, you can switch to run using compute task with reusable compute server, and that provides you the fastest possible execution for short duration jobs that is currently available within Vaya. So by aligning your workload with appropriate execution method, you can unlock better balance between performance, cost, and the end user experience that your users on Vaya can see. The second use case, the second best practice is implementing scaling controls for reusable compute servers. So by default, a reusable compute server scales when 100% of the pod in the pool is utilized, and it also scales up by 1 pod at a time. So imagine the scenario where all the pods are being used and there are a lot of concurrent heavy requests that come in, right? So a new pod is spun up, it is going to take this cold start delay as I referenced earlier. So there will be some job where there will be wait time to get that job created and this job executed, right? So you can basically proactively use 3 new parameters that we have added to the compute context, which helps you proactively scale up. And let me explain each of these attributes. Server pool scale threshold, it basically controls how the pool scales up based on a threshold of the pool utilization. So if you set a value of 80, that means when 80% of the pods in the pool is utilized, you can proactively scale up. And similarly, server pool scale step attribute controls by how many servers you can scale at a given point in time. So default is 1. So if you set a higher value, that means you can scale up by that many number of pods in advance and make sure these pods are already created and available in the pool to handle this concurrent user request. And server max available is the attribute that controls maximum servers that can be in the pool at any given point in time, basically giving you control over the maximum pool size and cost. So by setting a proactive threshold, you are injecting warm servers into the pool in defined steps and preventing user wait times during the burst of analytical activity. And the next best practice is basically proactive capacity management. Here we are talking about the nodes in the compute node pool, right? And when we talk about scaling a node, we need to consider the cold start delay of starting a node into the pool, right? It varies among cloud providers. In Azure, for example, it takes between 5 to 9 minutes to spin up a new node and add it to the compute port. So the best practice is to enable a new capability that we have added in SaaS Workload Orchestrator called time-based minimum node scaling. So if there are peak usage windows, you can use this time-based minimum and set a baseline that ensures that there is always that many nodes which is proactively scaled and available in the node pool. And by ensuring that Kubernetes clusters are pre-provisioned, that necessary compute capacity is available before the peak window hits, and you can provide a predictable performance to your end users, as well as you can optimize cost efficiency during the off-peak hours. So this is definitely one new functionality that we rolled out early this year as part of our 2026-01 cadence release that you can implement. So finally, I'll leave you with a performance checklist of supercharging your STP performance. Number 1, enable reusable compute server pool. This basically prevents the 5 to 10 seconds cold start delay that I spoke about for every job. Number 2, enable scaling controls for reusable compute servers. So this improves performance under heavy load by spinning up reusable compute servers faster and in batches. Number 3, set execution task parameter to true for all your micro workloads or short duration jobs to execute via compute task. So this basically forces a synchronous call that bypasses the traditional job execution service-based overhead. And finally, monitor your timeouts. Because compute task has a default 5-second timeout, ensure your job is optimized to run within that window, or you can ask administrators to change this default configuration up to maximum 30 seconds, and you can do that via environment manager settings. So I hope you learned some tricks that you can take back from this session and use it as part of your VIA migration. And I'm available at the theater if you have any questions. And yeah, please reach out to me if you have any questions or any feedback. You can reach out to me on my email address as well. And here are some additional resources that you can scan. These are some pointers to our help documentation, as well as some blogs our colleagues have written. It covers all the topics that I discussed today, starting with compute task, the STP server session capability, scaling the reusable compute servers, as well as time-based minimum node scaling documentation. With that, thank you all so much for being here and being part of this session. Hand it over to Kobe.
Thank you. And for those of you, if you weren't able to grab the QR code, the session is available in the app as well. The slides are there. So thank you.
Thank you all.